And our final senior thesis presenter this morning is Evgeni Aizenberg. His advisor is Professor Irving Bigio.
Thank you, Professor Pisano. Hello, everyone. My name is Evgeni Aizenberg, and I will be presenting my thesis on automated detection of colon precancer based on in vivo endomicroscopy images. My advisors for this project are Professor Irving Bigio and Dr. Eladio Rodriguez-Diaz. So first, I would like to start with some background information about colorectal cancer. CRC, colorectal cancer, is the second leading cause of cancer-related deaths in the United States in both genders, male and female. It is second after lung cancer. And as with any types of cancer, early detection of this disease is crucial for successful treatment. In fact, the American Cancer Society guidelines suggest periodic screening beginning age 50 to prevent the disease. So really the aim is to detect a precancerous state early on, so that you don't get to the stage where a patient has cancer. Now, the standard screening and prevention technique is colonoscopy. And colonoscopy provides physicians with a superficial view of the inner lining of the colon. Now, the challenge is that what physicians can see in colonoscopy is abnormal growth, which is called polyp. And you can see an example of a polyp here on the image on the right. The challenge is that the majority of the polyps in the inner lining of the colon are in fact benign. Some of them are potentially malignant, but colonoscopy does not provide sufficient information. In many cases, colonoscopy does not provide sufficient information to assess whether a given polyp is in fact benign or precancerous. And therefore, it has to be surgically removed, sent to histological examination, and then the underlying pathology can be evaluated. However, with nearly half of all removed polyps being benign, this gold standard approach is highly ineffective because there are a lot of unnecessary surgical interventions, it's time expenditure, and it's cost. Therefore, there is high demand for a real-time diagnostic technique that would be reliable, that would allow physicians to say on the place when they're doing the colonoscopy procedure on the patient, we see a polyp. Is that polyp premalignant or is that polyp benign? Now, in the mid-2000s, a new endoscopic imaging technique emerged called probe-based confocal laser endomicroscopy, PCLE. Now, PCLE system consists of a confocal microscope that is integrated in a mini fiber optic probe consisting of tens of thousands of optical fibers. This probe can be inserted into the working channel of standard endoscopes, meaning that you can use this probe in colonoscopy procedures. The optical properties of a confocal microscope are such that light collected by PCLE probes originates from a thin optical plane on the specimen. Now, that means that if you use PCLE to image the inner lining of the colon, for example, what you see are thin slices of the colon tissue, and the result are images that resemble, in fact, en-face histology slides. En-face histology slides mean you're looking from top down. It's a top-down view in the colon tissue. So notice here we have an example of a PCLE image. This is an example of healthy tissue. And it's characterized by these regular circular objects which are called crypts. And in fact, they will be important later on during the presentations, so just keep that in mind. And the histology slide shows a very similar structure. We again see a regular repetition of circular crypts. Notice also these oval-appearing objects within the crypt. Those are called goblet cells. And the same, maybe not seen that clearly right now here with the lighting, but they appear as black oval objects on the PCLE image. So very similar images, and the conclusion is that PCLE provides you with real-time in vivo histological information. There are several PCLE systems that exist on the market right now. The one which is relevant to this study is the Salvisio system, which is manufactured by a company called Mauna Kea Technologies in France. It has a lateral resolution of 1 micron, an axial resolution on the order of 100 microns, magnification on the order of 1000, and a frame rate of 12 frames per second. As I mentioned, what is the upside? You have real-time in vivo histological information. So you would expect this to be able to replace the gold standard, where you have to take out the polyp, send it to histological examination. You would expect that this could give you real-time histological information, and a trained expert will be able to tell you on the spot whether something is benign or premalignant. However, clinical studies show that the diagnostic accuracy and inter-observer agreement between human interpreters is in fact inferior to the gold standard. But again, the histological information seems to be there. So if humans cannot do the job, can a computer do the job? That's where my project comes in. And the aim of my project is to develop a method that can detect colon precancer automatically based on single-frame PCLE images. So translates into a typical classification problem. PCLE image on the input, we perform some feature extraction, input those features into a computer classifier, and receive a diagnosis on the output. Now, before I go into discussing feature extraction, I would like to give you a perspective on what kind of data are we working with. On the left here is an example of normal colonic tissue. So once again, characterized by regular crypts, these circular objects, and they also have this point-like appearing lumen in the middle, the center. Now notice when we go to benign tissue, these objects right here, those dark lines, those are crypts, but they have changed, and the lumen becomes kind of star-shaped. When we go to dysplastic, and dysplastic means high risk of malignancy. So it does not mean that it's cancer. It's very important to understand. Dysplastic means a very high chance of becoming cancerous. When we go to dysplastic, the crypts tend to have this rod-like shape. They have very dark appearance on the images, low image intensity, and they occupy a large portion of the field of view. So all of these features I mentioned above are important because we're going to try and use that. So first of all, intensity. Here I would like to note PCLE is a fluorescence-based imaging technique. It means that you use a contrast agent to produce the optical signal that you record. And clinical studies have shown that dysplastic tissue tends to uptake less fluorescent. Less fluorescent means less fluorescence, meaning lower image intensity. Therefore, as you can see in this example, we have a benign image. Here's a dysplastic image. You can clearly see that the overall image intensity of the benign image is much higher than the overall image intensity of the dysplastic image. To characterize this trend over a large population of PCLE images, the cumulative intensity distribution was computed over a set of 159 images. This graph shows the cumulative intensity distribution of 73 benign cases. Now, just what does that mean? Well, let's take, for example, intensity value of 50. If you take intensity value of 50, you go to the curve of a specific image. There are 73 images plotted here. The curve will tell you how many pixels in that image have an intensity value below 50. And the count here is normalized to the area, so it goes from 0 to 1. Now let me show you the graph for the same kind of plot, the cumulative intensity distributions for the dysplastic images. These are 86 dysplastic images. I will now intentionally flip twice between the two. Notice again, benign, dysplastic. Benign, dysplastic. So what we see is that in the dysplastic case, there's a noticeable hump in the lower image intensities, specifically in the range of 25 to 75. There's a peak increase rate in that range. For the benign cases, the peak increase rate is somewhere between 75 and 125. And this is precisely consistent with the clinical observation that dysplastic images tend to have lower overall image intensity. So it seems like a good feature, but there are 256 points here for each curve. So it is of interest to perform dimensionality reduction. In order to perform dimensionality reduction, the discrete cosine transform, DCT, was applied to each of these curves. And it was found that retaining the first 4 DCT coefficients can preserve the distinguishing trends and at the same time provide good classification performance, as I will show later on in the presentation. To illustrate that, this is a plot of the same 73 benign cumulative distribution curves, but the first 4 DCT coefficients were retained and the inverse was taken. Now the same for the dysplastic cases. I will intentionally flip again between the two, benign, dysplastic. As you can see, once again, for the dysplastics, the trend that the peak increase of the CID curves occurs at lower intensities is preserved. And we're using just 4 DCT coefficients. So very efficient dimensionality reduction on the order of 10 to the second. The next type of features used was spatial distribution features. And that again comes from the fact that benign and dysplastic crypts differ in shape and spatial distribution. In this benign case, the crypt is, there are 2 crypts that appear here. One of them corresponds to this dark line going across horizontally, the other dark line going across horizontally, and the goblet cells that surround the lines along the perimeter. In the dysplastic case, it's basically almost the entire image. The shape is completely different, and also the spatial distribution is completely different. So it is of interest to characterize it quantitatively. Notice that in both cases, benign and dysplastic, the cryptal regions correspond to the darkest areas in the image. This means that you can model them as local intensity minima. So a gradient-based segmentation algorithm was applied. Now to put this in perspective, here's an example where we take another benign image and we consider it as a 3-dimensional topographic surface. We plot the intensity along the z-axis as a function of position x and y. And again, the cryptal regions, which here is the vertical line right here, and there are 2 more crypts that appear on the left, they correspond to valleys and basins. Again, local minima of the intensity function. So the following gradient-based segmentation algorithm was applied. Regions of interest correspond to local minima, so we smooth the original image with a 10 by 10 Gaussian filter to make the surface more continuous and remove some noise. Then the partial derivatives along the horizontal direction and the vertical direction are computed, and only those points where the partial derivatives have a value between -1 and 1, in other words, close to 0, and the intensity value is below the mean, are retained. The results are as follows. Here are examples. Here's the image you saw before, an image of a benign crypt. These are the points that get retained, so that's pretty good. This is another case where we have an image of a dysplastic crypt, premalignant. And the segmentation works pretty well here. To characterize quantitatively those regions that got segmented, 2-dimensional moment invariants were used. These moments are invariant to translation, scale change, and rotation. As I will show in just a couple slides, it was found that using just 4 moment invariants is good enough to provide good classification performance. So the classification experiments were as follows. We used the same data set of 159 PCLE images. 73 images were benign, 86 represented dysplastic tissue. The intensity and spatial distribution features were combined to train a linear support vector machine classifier. And training and testing were done under leave one out cross-validation, since, as you can see, the data set is limited in size. So that's a standard approach to go, where at any given experimental session, the entire training set except for one sample is used for training. I'm sorry, let me say that otherwise. The entire data set except for one sample is used for training, is removed, and once the classifier is trained over the training set, it's tested over that removed sample, and you repeat that procedure for all of the samples in your data set. Before I show the results, I would like to introduce several statistical measures which are relevant to this study. First is classification accuracy, very simple. Simply the number of samples classified correctly over the total number of samples. Now, the three following statistical measures are defined in terms of true positive, false positive, true negative, and false negative. Now, the definitions are there. I will not bother you with the formulas. I will just tell you what this means. Sensitivity is a measure of the fraction of positive cases that were identified by the system as positive. In other words, the fraction of dysplastic cases that were identified by the system as dysplastic. Specificity is an analogous measure for negative cases. The fraction of benign cases that are identified by the system as benign. And negative predictive value measures what fraction of cases identified by the system as negative are in fact negative. In other words, the trustworthiness of saying that a person is healthy. The results were as follows. For classification accuracy, here what's plotted is the accuracy as a function of different combinations of features. Each row corresponds to a different number of DCT coefficients used for the intensity features, and each column corresponds to a different number of two-dimensional moments used for the spatial distribution features. The maximum classification accuracy value attained was 91%. However, note that here in the central area, the variability is not that high at all. We're talking about 89%, 90%, 91%, and there are different combinations that give the highlighted maximum value of 91%. For sensitivity, the maximum value attained was 95%. Specificity, 92% maximum value, and negative predictive value, 94%. So to summarize this, best performance achieved with 4 DCT features and 4 moment features, giving a sensitivity rate of 95%, specificity of 86%, and negative predictive value of 94%. What kind of conclusions can we draw from this study? 2 things. The study shows that the results are in good agreement with histopathology. They're in good agreement with the underlying truth about the tissue, whether something is dysplastic or pre-malignant, or whether something is benign. So this is good. The diagnostic accuracy is comparable to what is shown for human interpreters in clinical studies. It is important to note what kind of future work should be done. First of all, algorithm refinement. The segmentation algorithm should be improved since it's not 100% robust. It is also of interest to incorporate localized features such as texture, and larger data sets are also crucial for statistically significant results. Above all, a comprehensive study is necessary that would answer the question whether computer-based classification of these images can outperform human interpretation. And such study would involve a large number of patients, real-time diagnostic of PCLE images by a physician, and then presenting the same images that the physician diagnosed in real time to a computer-based classifier. That's a fair game. And then, once you have the statistics, you could argue about the computer-based classification being worse or better. The significance of this study is that it is among the first, it is not the only one, but it is among the first attempts to develop a computer-based automated classification technique for this problem. And it does serve as a proof of concept that yes, you can indeed achieve performance which is in good agreement with the histopathology and is comparable to human accuracy with these images. I would like to take this opportunity to sincerely thank my advisor, first of all. Advisors, Professor Irving Bigio and Dr. Eladio Rodriguez-Diaz, for their continuous and essential advice, support, and guidance along the way throughout all of the stages of my project. I'm very thankful to the entire Biomedical Optics Laboratory for their warm support and all the advice they had. And last but not least, I would like to thank my family for lots of words of wisdom along the way, and especially my father, Igor Aizenberg, who has been my lifelong mentor, both in science and life as a whole. And that's it. Thank you very much for your attention. I'll be glad to answer any questions. Yes?
The PCLE instrument, what is the depth of detection? Are you only seeing surface histology, or are you actually...
What you see, in fact, for a given frame, the information that a single frame presents is collected from a slice that has a thickness of about 50 to 70 microns. 50 to 70 microns. And there you can go in a couple steps below and above. Yes, Professor Conrad.
I have two questions. One, what was the motivation for choosing DCT as opposed to Fourier, wavelet, any other transmitters? These were known for compression properties, but not so much for representation used in, let's say, feature characterization.
The discrete cosine transform is known to have very good decorrelating properties that are shown, in fact, to be close to the principal component analysis Kernel-Liouville transform, and so they provide very efficient decorrelation, and it is clear why the first 4 DCT coefficients, for example, in this case, let me just go to that slide real quickly, why they can describe the properties well, because we're talking here about low frequency content. We're trying to characterize these peak increases, which are in low frequency content, so looking at low frequency DCT components does the job. It is definitely valid to look at other techniques to characterize, though DCT is more compact than the Fourier transform, and I think it is definitely valid to look at other choices, but in my opinion, 4 DCT coefficients seems like a very good description. And if you look at the scatter plots, in fact, for just the intensity features, you see a very evident separation in space between dysplastic cases and benign cases.
So related to this, you're combining let's say 4A number of coefficients from DCT with your partial derivatives.
Yes.
In your segmentation. Putting it into one long vector and throwing it as SVM. So now, are you normalizing in some way between the DCT coefficients and your derivatives because they are apples and oranges? One is the coefficient value in frequency space, and one is a partial derivative in space. So numbers are completely different. Did you normalize them in any way?
So just to make sure we're on the same page, so the DCT, in fact, the detail about the DCT coefficients, once the DCT coefficients are computed, they're converted to log scale because that decreases the dynamic range, makes the picture clearer. For the partial derivatives, it's not exactly partial derivatives. You use the partial derivatives for the segmentation stage. Then the features themselves are the 2-dimensional moments. Yeah, right. That's true. That's true. I don't necessarily, maybe you can change my mind here, but I don't necessarily see a problem in the different axes of your space, basically, being apples and oranges here, because each variable represents something else. And it's quite standard in the classification problems that this happens. It is worth looking whether it is necessary to perform such normalizations to some dimensionless quantity, but I don't necessarily see a problem right away. Thank you. Yes.
One more, because we're starting to run late. David?
Just so I understand the training process, you had a sample set of data and you leave one sample out and then you train and then you update the training parameters, pushing through that one that you leave out. Was there any part of the data that was reserved solely for testing, or was all the data going into training and then
It was like the second way that you mentioned. It was in fact all of the data going, and that's really solely due to the fact that we were working with a limited amount of data available. So in order to ensure that as much samples participate in training, we had to go with leave one out cross-validation.
Do you think there is a significance of leaving some data out that you don't use for training that you can test against so that it's not influenced by the training process? So
you mean like having a separate training and testing set in general? Yes, absolutely. In fact, for really a proper study, there should be a larger data set and there should be completely separate training and testing sets and no leave one out cross-validation, because really to obtain results that could show the significance of this and the applicability of this in the clinic, you need to go with completely separate independent training and testing sets.
And it also seemed like you had about half samples that were benign and half samples that were malignant, roughly?
Roughly, yes.
Is that a fair sample of what you expect to see in real life, or is it that's what you
fairly...
In terms of the rates, I guess, you expect to see it?
I don't want to give you the wrong statistics, however, I would say fairly yes, because the reason in the first place why PCLE is used in a specific polyp is because the experts are not sure when they see the polyp for the colonoscopy. So yes, in many of following the polyp statistics, you would expect that the majority of the polyps would still turn out to be benign. So you would still have the majority being benign and the minority of them being having a malignant potential. Yeah, it's a good point actually to look into that and look into the significance of having the right proportions. Thank you.
Thank you.
Thank you very much.